Hello, dear student. Assalamu alaikum. This lecture is about the topic of threat to different type of threats to internal validity, right? In our last video lecture, we covered the topic of what is internal validity and what is external validity. So in case you have forgotten or currently you can't recall what is internal validity, I would like to, request you to have a recap of my last video and watch and understand the concept of internal validity. So here in this lecture, today's lecture, we start with a third type of threat to internal validity. Actually, whenever we run regression, first of all, let me say that we did the first two types of threats to internal validity in the last video lecture. And today we are covering the third type of threat to internal validity. So what do we mean by a threat? That means that when there are some issues in the regression, which we are going to discuss, some of them today and some we discussed in the last lecture, that when there are some issues in the variable or in the regression model, then the results, they are not, consistent or reliable, or maybe the regression results are sort of questionable. So the third type of error that can influence the efficiency of a regression model, or that can be a peril or a threat to the internal validity, is the measurement error and errors in variable bias, right? Okay, so what is measurement error and errors in variable bias, right? For example, if I help you recall the scenario where we were regressing test score on student-teacher ratio, like how test score in a class depend upon student-teacher ratio. So, for example, if this scenario requires the use of data for classes 1 to 5 or grade 1 to 5, right? What am I saying? That I have to regress test score on student-teacher ratio, and my aim is to analyze the determinants of test score in grades 1 to 5, or my aim is to analyze the relationship between test score and student-teacher ratio in grade 1 to 5. Okay, so now what happened? Let's say I have data on test score or of 1 to 5 grader students, and in student-teacher ratio, let's say by mistake, instead of taking the data of students from 1 to 5 grade, I take the data for students of 6 to 10 grades. So this is a mistake, right? Instead of using data for 1 to 5 grades, we have used data for 6 to 10 grade students. So this is an example of measurement error or errors in variable bias, that we have error in this variable, which is student-teacher ratio. Okay, so what happened when this type of error is introduced? This should lead to a bias in the estimated coefficient, and that bias will be so, you can say stubborn, right? That it will remain even in the large samples. That's why we say that not only the estimates will be biased, even in the large sample, they will not converge to the actual population betas. That is, if I come back to this equation, if I have an error in this student-teacher ratio data, so no matter how large a sample I take, this beta 1 hat coefficient will never be a good estimate of beta 1, where beta 1 is a slope coefficient that is required to relate fifth graders test score and the student-teacher ratio, right? Beta 1 is required to estimate the slope coefficient or the relationship between the test score of the fifth grader and the student-teacher ratio of the fifth grader, right? Remember, it must contain fifth data, both side fifth grader. But now we have an error. We have induced this student-teacher ratio, we have induced an error into it. So beta 1 hat will never converge to its desired value beta 1, right? So when there is error in the independent variable, it leads to biased estimate as well as inconsistent. Okay? Just in case you don't remember, or just a fallacy, that if you don't remember, inconsistent simply means that even if in the large samples the sample results, they are not converging to population results, then they are inconsistent. Or even in the large sample, if beta hat is not converging to actual population beta, that means this beta hat is inconsistent. So by now I have established that when there is measurement error in the variables, the betas become biased and they become inconsistent. Okay? Okay, so what are the reasons for measurement error, by the way? I mean, why do we, get such type of data that is prone to errors, right? So there are multiple types of or multiple sources of measurement error. For example, it may be subject to recall error. For example, if in a different scenario we have to get data on the last year family income of a household, and if you're asking a person and he's unable to recall the exact family income, so he or she will be quoting an approximate or a rough idea, right? So this is inducing a measurement error into our result, that our target was to, get the exact value of last year's family income, but the respondent is giving me a crude or a rough estimate. So now we have the problem of measurement error. Another example, intentional misreporting. For example, if you ask people about their income, they may be hiding, let's say, 20%, or they can hide any percentage, but just hypothetically, if they hide 20% of their income because they are afraid that we'll be taxed more if we report our actual income, right? So intentional misreporting also is a source of measurement error, right? So there can be, a multitude or a diversity of reasons behind measurement error, that why do they occur. Okay, next we have to prove that measurement error results in correlation between the regressor and the error term, right? What does that mean? That when we have measurement error, there is a correlation between the x variable and the residue, right? So if you can recall from the concept of omitted variable bias, we also studied this issue there. And what happened there? Whenever the x or the regressor is correlated with the error term, we have the problem of endogeneity, right? So let's prove it here that we have measurement error, then there is a correlation between the regressor and the error term, and consequently there is the problem of endogeneity. So suppose that there is a single regressor x, let's say actual earnings, right? That we have a single regressor or a single x variable, and let's say that variable is actual earning. But that x is replaced by xi tilde. This symbol over x is read as tilde, right? So if xi is replaced by x tilde, and what is x tilde? Reported earning. Like people are trying to hide their earnings, so instead of quoting their actual earning, they are giving you data on something else, which is sort of, and maybe they are hiding a part of their actual earning. So that's why what's being reported is xi tilde, which is reported earning. Okay, so because xi tilde, not xi, is observed, the regression equation estimated is, actually what is our target, that y should be regressed on x, right? This is a target, and this PRF simply stands for population regression function. Okay, so this is your target. Now, if I just simply add subtract beta 1 times xi tilde into this equation, right? And why am I adding subtracting? Because I want to analyze the impact of measurement error. So what I have done, I've added beta 1 xi tilde, and I've also subtracted the same quantity. So that means there is no difference. This is the same equation. And simply by rearranging a little bit, that is, I write this part as it is here, and then I take beta 1 common, and so xi minus xi tilde plus ui. Okay, so this particular part, this is read as another type of an error, VI. And why am I calling this entire thing as an error? Because UI is, inherent error or the residual in the original regression equation. And this part is an error due to the difference between the actual X and the reported X, right? This may be the difference between the actual earning and the reported earning, right? So this error, this entire thing is, let's say we call it VI, right? So the population regression equation written in terms of xi tilde has an error term VI. That is, now what is this VI? It is a function of that measurement error. See, this VI, this contains xi minus xi tilde. So this error VI is a function of the measurement error, which we defined as the difference between the actual X and the reported X. So this random error is correlated with the measurement error, right? So this proves that what we were trying to establish, that in the presence of measurement error, the regressor xi tilde and the error terms, they become correlated. And by virtue of the topic covered in omitted variable bias, you can recall that whenever the regressor and the error term are correlated, we have the problem that the betas or the estimated coefficients are biased and inconsistent, right? Okay, so next we start the fourth type of threat to internal validity. Okay, so the fourth threat is if we have missing data or we have sample selection bias, right? So missing data can have three different scenarios. Case A is when the data are missing totally at random. Okay, that is, there is no fixed pattern, data is missing at random. Case B, when the data are missing based on X or the independent variable, right? We will discuss these in detail one by one. Case C, when the data are missing because of a selection process that is related to the dependent variable. Okay, for now, if you don't understand what are the repercussions of these cases, we will discuss these cases one by one. Okay, so let's start case A, which is data missing at random. This causes a reduction in sample size. So what happened? For example, if you were targeting a data of, let's say, 100 respondents. So, but randomly, suppose data of 13 respondents is missing, right? So you will be left with 87 sample size. So, but whatever the reason, your data has been reduced, but still beta remain unbiased and consistent. Why? Because the missing data has no fixed pattern. It's not that high earners data is missing or low earner data is missing. It's simply random, right? Like, for example, out of those 13, it may be the case that 5 are high earner, the other are a mix of medium and low earner. So that means still the remaining 87 sample size is still a good representation of all types of earner, like the low, medium, and high earner, right? And by the way, in the comment section of this video, I will also type in my personal email ID so that those of you who are watching it and trying to make use of these videos, if they have any detailed queries, they can always reach me out, email your query, and I will, respond. The response time may be like 3 to 4 days, but I will definitely respond to whatever the focused queries I receive. Okay, so the case A was data is missing at random, and as I said, when the data is missing at random, that means there is no systematic error and beta remain unbiased and consistent. So only thing when we have a reduced sample size is that our sample size must be greater than or equal to k plus 1 whole square. This is simply a rule of thumb for the minimum sample size required. So what does that mean? For example, if you are running a binary regression, which means you simply have 1y, 1x, So k is the number of x variable, so k will be 1. Now 1 plus 1 square is 4. So the minimum sample size required to run a binary regression is 4, right? Now you may have a question that how can we run a regression with just 4 pairs or 4 observations? What I'm saying is this is the minimum possible sample. Of course you have the more than 4, that is, very good, and it will offer more efficiency in the results. But this is just giving me a bare minimum sample size required to estimate a regression having k independent variables. So for example, if you, instead of a binary regression, if you have 1y and 3x variables, right, then your minimum sample size required will be n must be greater than or equal to 3 plus 1 whole square, that is 4 square. So minimum sample size required in that case, when you have 3 regressors or 3 independent variable, the minimum sample size required will be 16, right? 3 plus 1 whole square or 4 square comes out to be 16. Okay, so next we have case B, when the missing value are on the basis of the regressor X, right? So let's say if I come back to that example where I was discussing the relationship between student-teacher ratio and their test score. Let's say in that regression, if we included data of only those schools or those districts in which the student-teacher ratio exceeds 20, right? I have applied a filter on the data, right? What type of a filter? That I'm including only those districts or only those schools where the student-teacher ratio is greater than 20. So now what will happen? My results will be generalizable only to those cases where this condition is met, right? What am I saying? That if I apply this filter and I get some values of beta naught and beta 1, let me go to the previous slide just for a moment so that I can, for example, I'm discussing this regression, okay? What am I saying? That if I apply a filter, that I'm going to have data of only those districts where student-teacher ratio is greater than 20. So what will happen? These beta naught and beta 1, if I get the numerical values after running the regression, they will be, only generalizable to all those type of schools or districts where student-teacher ratio is greater than 20, right? Simple. That the data we have analyzed, we can use it to generalize similar type of settings of population, right? So now what will happen, once again, coming back to that case B discussion, okay, right? So based on such regression, we won't be able to generalize the results for the districts or schools where student-teacher ratio is less than or equal to 20. In other words, my sample size has once again reduced. Why? Because whenever I apply a filter, you see I applied this filter. The student-teacher ratio exceeds 20. So I have sacrificed some data. Some of the schools or the district where student-teacher ratio was less than 20, I have deleted those observations. So once again, my sample size has reduced and my results are generalizable only to those districts where student-teacher ratio is greater than 20. But still, my results, if I generalize them for the correct type of district that is meeting these conditions, then still my beta will be unbiased and they will be consistent. Yes, excuse me. Okay, so next we have case C. Case C is then when we have data that is missing because of a selection process that is related to the value of the dependent variable. Now we have a problem. Why we call this a particular problem? Let's say if I refer back to that example of earnings where I was discussing that you have to get data on earnings, right? So I'll just give an example here. Okay, so let me discuss one example. Suppose I want to regress earning on experience, age, and qualification. That how much you earn depends upon how experienced you are, what's your age, and what is your educational qualification. And you know that random error is always there in stochastic or the statistical models. Okay, now if the data of, let's say, experience is missing for all the high earners, right? So now what will happen? The missing data is dependent upon the values of earning. That is, the missing data is in accordance with the values of y variable, right? Missing values corresponds to all high earners, or missing values are according to the y variable or the dependent variable in the above regression. Okay, so if this type of scenario happens, that means that intentionally I am excluding all the high earners from my sample. So now the error term will become correlated with the regressor, and the repercussion are the same as the omitted variable bias. That is, betas become biased and inconsistent. Okay, so next we will discuss an example of you see missing data and the relevant concepts. Okay, so we'll discuss the example in which you will see how missing data can influence the regression results. Okay, so we have a typical case study or a typical example. Do stock mutual funds outperform the market? Right? So to understand, let's see or understand what are stock mutual funds. These are investment vehicles that hold a portfolio of stocks. By purchasing shares in a mutual fund, a small investor can hold a broadly diversified portfolio without the hassle and expense of buying and selling shares in individual companies, right? So you're purchasing the mutual funds so that you avoid the hassle of purchasing individual shares, right? So you automatically become a member of a diversified portfolio if you invest in a stock mutual fund options, right? So some mutual funds simply track the market. For example, by holding the stocks in the S&P 500, whereas others are actively managed by full-time professionals whose job is to make the fund earn a better return than the overall market, right? So we have those type of proper consultants that handle and manage a particular type of stock. Okay, so the question is, do these actively managed funds achieve this goal? That is, do they earn better returns? Let's say we want to test this empirically. So one way to answer this question is to compare the future returns on mutual funds that had high returns over the past, right? That is, if they were earning higher in the past, is there a guarantee or a high probability that they will earn better in the future as well, right? So that type of prediction we want to make. So in making such comparison, financial economists know that it is important to select the sample of mutual funds carefully. Why? This task is not as straightforward as it seems. Some databases include historical data on funds currently available for purchase. No, but those of you who have followed a little bit of activities or the conventions in the stock market, you know that the stock that who are performing poorly, they are all often kicked out of the market, and that's why we use also the phrase dog, right? The poorly performing funds are the dogs. We don't have data for them. Why? Because they literally had sometime they went into a merger with some other businesses. It's fairly possible that for a particular set of years, for example, for 5 years, a dog who's currently a dog, but in the past that stock was performing very well, and we can have the data of the first 10 years, and that can be higher returns. But 10 years down the road, something terribly happened with that stock and it became a poorly performing fund. It became a dog and it just kicked out of the market, or it just got merged into other funds, like some other brokers, they purchased that type of a stock. So what will happen if we have these type of stocks that are more poorly performing? We will have missing data for those type of funds, right? Okay, so for this reason, a study using data on historical performance of currently available funds is subject to sample selection bias. Now, what does that mean? The sample is selected based on the value of the dependent variable returns. Why? Because the dogs, or which particular entities were called as dogs, whose funds were like the funds with the lowest returns, they were eliminated, right? So the dependent variable is return, right? We are analyzing the determinants of returns, stock returns. But the companies or the funds that had lowest return, they got eliminated out of the market. So now you can see that the cases we were discussing, now you can easily understand this is case C, right? So under case C, the betas, they will be biased, and the betas, they will be inconsistent. That is, even in the large sample, they won't give us good results. So financial economists refer to this type of selection bias as the survivorship bias, because only the better funds survive to be in the data set. So when financial econometrics correct for the survivorship bias by incorporating data on the defunct funds, like the dogs, if we get data, include the past data of the dogs or the underperforming funds right now, then you see, if you analyze that type of data, the empirical evidence suggests that actively managed stock mutual funds do not outperform the market on average, and that past good performance does not predict future good performance. So this is the reason there is so much uncertainty in the market, that it's not a guarantee that if in the past you have been earning good, uh, or you had a particular stock has been performing well, no guarantee it's going to perform good in the future as well. Currently, in this this particular scenario, or a structural break of COVID-19 or the coronavirus, most of you can unfortunately readily understand this, that some of the stocks, they were performing really well, but now because of the structural break, there's a terrible performance, right? So you can possibly see that the current, many of the past good performer, or the good funds that yielded high returns, they will ultimately emerge as dogs. And maybe 5 years down the road, we don't have data for those type of funds. So this was a practical example of this case C, which was data is missing because of a selection process related to the value of the dependent variable. So here the selection process, or the returns of those firms were missing, that performed poorly in the market. Okay. So next we start the fifth type of threat to internal validity, which is simultaneous equation bias, or indigeneity. So simultaneous equation, as the name suggests, that originally regression is aiming for this type of a model where y is a function of x. But what happens if x in turn is a function of y? So we have bidirectional causality. So we call it simultaneous equation bias. So how to solve this type of a problem? There are two ways to control the simultaneous equation bias, which I have abbreviated here and onward as SCB. So there are two ways to control or mitigate SCB. The first one is instrumental variable regression that we will be discussing shortly, and the second one is to implement a randomized control experiment, which is currently not included in this video. So let's focus on the instrumental variable regression, and this is from the chapter 12 of Stock and Watson regression book, right? And if you want to see the complete title of that book, let me show you that as well. Okay, so here is an image of that book, right? Chapter 12 of this book, Introduction to Econometrics, updated 3rd edition. And by the way, you can easily download this book from the Genesis library. Let me show you the URL. So from this particular URL or the website, you can download that book that I've just mentioned, right? This is the URL. And if just in case you can't see this, let me show it in a bigger font here. So from this online bookstore, you can download that book that I have just discussed, Stock and Watson book, right? This book. Okay, so I am covering chapter 12 of this book here in instrumental variable regression topic. So instrumental variable regression is a general way to obtain a consistent estimator of population betas when the regressor X is correlated with the error term. Actually, when this happens, endogeneity, that when X is a function of Y, Y is a function of X. So we have bidirectional relationship, right? Then we use the methodology of instrumental variable regression. So let's start a simple, understanding of instrumental variable regression where we have one y and one x. Okay, so if x and u are correlated, the OLS estimator is inconsistent. That is, it may not be close to the true value of the betas even when the sample size is very large. This you also already proved in the omitted variable bias section when we were discussing that if when x and u are correlated or we have the issue of endogeneity, the OLS estimator is biased and it is inconsistent. Okay, so the correlation between x and u may stem from different sources, for example, due to measurement error, due to simultaneous causality, or due to omitted variable bias. So whatever the source of endogeneity or the correlation between x and u, you can solve that or address that using the instrumental variable regression, right? So what is instrumental variable regression? It is if there is a valid instrument variable z, the effect on y of a unit change in x can be estimated using the instrumental variable. So let's not get lost in this fancy terminology. What I'm saying is, originally I want to see the impact of x on y, right? I want to see the impact of x on y. But the problem is I have the issue of endogeneity, that is y is a function of x, x is a function of y. So what can I do? I can use an instrument z, and by using this instrument I will obtain the effect on y of a unit change in x. That is, I still be getting the same beta which will represent the relationship between x and y, but I will be using this instrument. So how to do that? Let me explain. First of all, the instrumental variable, its assumption and some terminology, and then we will see how to use it. So recall that the original regression equation that we were targeting was y as a function of x, so that's why you have this type of an equation. So variables that are correlated with the error term are called endogenous variable, and the variables that are not correlated or uncorrelated with the error term are called exogenous variable. Because this terminology you will face frequently in the textbooks or in the lectures, so I have to explain this, right? So whenever a variable is correlated with an error term, we call it endogenous. Okay, so we were discussing that we can use instrumental variable if we have a valid instrument Zi. So what are the properties of that instrument? The correlation between the instrument and the regressor is not equal to 0. What does that mean? Actually, we are sort of replacing Xi with this Zi, right? So this xi must be correlated with zi. I mean, it should be a good proxy, right? So the correlation should not be 0. And the correlation between the instrumental variable and the random error is 0, right? Why? Because the whole problem started from this, that the correlation between the regressor and error term is non-zero. But over here, instead of using that x variable, I'm using z variable. And what are the two main properties of z? These two properties. That z is a good proxy of x, but still z is not correlated with u or the random error. So how we use it, let's say the first methodology, the two-stage least square method, often abbreviated as TSLS, right? So in the first stage, we decompose x into two components. A problematic component, that is, it is correlated with the regression error, and a problem-free component, that is uncorrelated with the error. Then the second stage uses the problem-free component to estimate beta 1, right? Which is unit impact of x on y. So let's explain this process, because in the first go it seems a little bit of complicated, but I'm sure once you go through these details, you will understand. The first stage regression begins with a regression linking x and z. So xi is a function of zi. So this pi naught and pi 1 is simply, this is the intercept and this is the slope, right? So now why I'm not using betas? Because this is a different regression. This is, instead of y on x, this is x on z. So in the first stage, I regress x on z. That is, I regress my current independent variable on the instrument, right? So this first part, you see, it has nothing to do with ui. So let's say this is the problem-free component. And this vi, this is the problem component, right? Okay. So the idea behind the two-stage SLS or TSLS is to use the problem-free component, that is this pi naught plus pi 1 zi, and to disregard vi. However, pi naught and pi 1 are unknown, so we have to estimate. So what do? We run a regression xi on zi, and we will get pi naught hat and pi 1 hat. That is the sample estimate of pi naught and pi 1. Okay, then in the second stage, we regress the actual y on xi hat. So what is this xi hat? These are the predicted values from step 1. That is, whenever you run a regression in step 1, you save the predicted values, right? You save the predicted values from first step in a separate column. So now you have a column of yi, that is your actual or initial dependent variable, and you have a column of predicted values of x from the first step. So now you regress yi on xi hat, right? So the resulting estimators from the second stage regression are called TSLS estimator or beta naught hat TSLS. You see, the actual aim was to see the relationship between yi and xi, but now we are, sort of proxy, using a proxy, and we are analyzing relationship between yi and xi hat. So that's why we call this as instrumental variable. So now you will think that how come this type of a regression will give me the desired results or the desired estimates for beta naught and beta 1, right? Okay, so let's discuss how instrumental variable works, like what type of a magic is done through this 2SLS that you can say that the betas are now unbiased and consistent. Let's say I'm referring to a particular researcher who actually proposed this technique of instrumental variable. So let's say Mr. Wright had data on QI butter, and that is the quantity of butter consumed, and PI butter is its price, right? Like we want to see the relationship between quantity consumed and the price. And if you have understanding of economics, or just you can go and analyze or use the resources on the internet, you can easily see that whenever we have a model which is regressed in the form of log on both sides, this is a log-log model. So in this type of a model, the beta 1, how is it interpreted? A 1% increase in the price of a butter yields a beta 1% change in demand. So in the terminology of economics, we call it demand elasticity, right? A 1% increase in the price of a butter yields a beta 1% change in demand. So beta 1 is the demand elasticity. Okay. So Wright, or Philip Wright, who proposed the instrumental variable technique, he had data on total annual butter consumption and its average annual price, right? So he had data on quantity consumed, or you could say quantity demanded, and its annual price, right? But he had a key insight. You see, because of the interaction between supply and demand, right? They are not independent. So the regressor ln of pi butter, that is actually the price of butter, it is likely to be correlated with the error term. So what am I saying? That price is a function of demand, but demand could be a function of price as well. So there is a bidirectional type of a relationship. That's why Mr. Wright said that supply and demand have interactions, right? So let's see what is meant by that. If in figure 12.1a, right, let me show you that figure first. You see, this is the figure 12.1a, and you see there are different types of demand, and this D1 represents demand in the first period, D2 demand curve in the second period, and D3 is the demand in the third period. And similarly, S1, S2, S3 are the supplies in different periods. Okay, so the demand and supply curve for the first period are D1 and S1, right? I would request that you keep on referring to that figure once you are learning. So the demand and supply curves are denoted as D1 and S1, and the first period equilibrium prices when D1 will be equal to S1. That is, market equilibrium is when demand and supply are equal. So going back to that figure, in the first period, D1, this curve, and S1, this curve, this is the period 1 equilibrium, right? But what happened? In period 2, suppose that the demand increases, right? So does the supply, right? So now the new equilibrium will be this point. So that's what is discussed here, right? So in year 2, as we were just discussing there, demand increases from D1 to D2 and supply decreases from S1 to S2. Let's say why? Because of an increase in the cost of producing butter. So the equilibrium price and quantity will be now different. So you see that demand and supply, they are interchangeably, or there are interactions between them. So this is the same concept as saying that there is a bidirectional association. That is, price is a function of quantity demanded, but quantity demanded is also a function of price. So how do you understand? For example, you see the simple law of demand is that your demand of a particular good depends upon what is the price of that good. But how the supplier set the price? If their product is in high in demand, maybe they will set a higher price. So that's why there are interaction between demand and supply, or price is a function of quantity demanded is a function of price. So we have an issue which could be resolved using the instrumental variable, right? So what could be the instrumental variable, right? So Mr. Wright realized that there is a way to get around this problem, to find some third variable that shifted supply but did not shift demand, right? That it is shifting the supply but not shifting demand. So for example, there could be different instrumental variable. For example, one could be weather, For example, below average rainfall in a dairy region could impair grazing and thus reduce batter production at a given price, so it would shift the supply curve, right? But such a change in rainfall, we assume that it is not going to influence demand, right? So the correlation between dairy region rainfall and UI would be 0, right? So if you are confused about this scenario, just go back to the original, requirement. The correlation between the instrument and included regressor is non-zero. So here in the case, so included regressor, just a minute, the correlation between the instrumental variable and the included regressor. So what does that mean? The correlation between that average dairy rainfall and the price of butter, it is non-zero, right? The supplier, how are they setting the price? If the average rainfall is much lesser, maybe they will set price accordingly. So the correlation between the instrumental variable and the included regressor is non-zero. But the correlation between the instrumental variable and this residual is 0. So that's how instrumental variable techniques can work, right? So next we have the formula for two-stage SLS or TSLS estimator. So as the first stage of TSLS is to regress xi on the instrument zi and then compute the OLS predicted value xi hat, the second stage is to regress yi on xi hat. Therefore, the formula for TSLS expressed in terms of xi hat will be covariance between x hat and y divided by the standard deviation of x hat square, right? If you can recall, the simple OLS beta 1 formula was covariance between x and y divided by variance of x. But now we are in the second stage regressing y on x hat, therefore we have covariance between x hat and y hat, x hat and y divided by variance of x hat square. So this is the formula for the slope coefficient under TSLS. Okay. So how do we define xi hat? If you recall, xi hat was simply y naught hat plus y1 hat zi, right? If you're just forgetting this, let me show you again the equation that related x and z. So this was the equation, right? So if I talk about the predicted or the fitted value of xi, you know that the predicted value ignores this part, the residual part, and the hats are applied on the coefficient. So we have this equation that xi hat is equal to y naught hat plus y1 hat zi. So the variance of x hat is simply y1 hat square and variance of z. Why? Because this y naught hat and y1 hat are some constant, and there is a property of variance that variance of a plus bx is equal to simply b square times variance of x. That's why variance of this xi hat is y1 hat square into variance of zi, right? Similarly, s or the covariance x hat y hat is equal to y1 hat s of zy. Now when we are applying the property on covariance, then remember that the coefficient that is multiplied is not squared, whereas in the property of variance that constant is squared, right? Therefore, beta 1 TSLS is equal to, we simply put on these values that the covariance between x hat and y is equal to this quantity, and the variance of let me see this. Okay, so covariance x hat y divided by variance of x hat square. So we put this variance of x hat square in the denominator and the covariance term in the numerator. So this is cancelled out and we are left with this, right? Covariance between z and that is the instrumental variable and y divided by pi 1 hat square and the variance of instrumental variable z. So pi 1 hat is the OLS slope coefficient from the first stage, right? So pi 1 hat is the OLS slope coefficient from the first stage. So pi 1 hat is the covariance between z and x, because remember that in the first stage regression we regress x on z. So pi 1 hat is SZX, that is covariance between z and x divided by variance of z. So why variance of z? Because now our independent variable is z, and in the denominator we always have the variance of independent variable. So beta 1 hat TSLS become, if I switch on this value of pi 1 hat here, I get this, right? Covariance between zy divided by covariance between z and x. So TSLS estimator of beta 1 is the ratio of the sample covariance between z and y to the sample covariance between z and x. Now we have the derivation of the large sample distribution of TSLS estimator. So remember that the underlying regression model, that is the actual regression model we were targeting, was y as a function of x. But then we converge towards the TSLS because of the issue of Indigeneity or simultaneous equation bias. But the underlying equation was this. So if I can write this yi and subtract y bar, so I can easily rearrange yi minus y bar equal to this. So the covariance between z and y is defined as, the formula for covariance is simply the summation of the cross product term, that is the first variable minus its means into the second variable minus its mean divided by n minus 1. Because we have samples, so we divide by n minus 1. Okay, so now instead of yi minus y bar, I write this entire quantity here. So this becomes, this step becomes this, okay? And then I separate out the two terms and I have beta 1 times this thing into xi divided by n minus 1 plus 1 over n minus 1 into sum of ui minus u bar into zi minus z bar. This is simply, expanding, just multiply and open this term. Okay, so then beta 1, and what is this? This cross product of z minus its mean, x minus n divided by n minus 1, so that means it's covariance between z and x. So I've written this entire thing as covariance, and beta 1 is as it is. Plus the second term, 1 over n minus 1 as it is, and then I am multiplying sum of zi minus z bar, once with ui and then with u bar, right? So then this term as it is, we know that the summation of sum of deviation taken from the mean is 0. So sum of zi minus z bar will be 0, because whenever you take deviation from mean and you add them, you will always get the answer as 0. So that means this term will be vanished. So we will be left with this thing, right? That's why we have this formula. Covariance between z and y is equal to this quantity. Okay? So that means beta 1 hat TSLS becomes covariance between z and y is replaced by this divided by covariance between z and x was actually there that we just covered. So covariance between z and x means this thing, right? Okay. So beta 1 hat TSLS is equal to, so now what I'm doing, this is covariance between z and x, this is also covariance between z and x. So if I separate out these two terms, the first one is beta 1 and the second one is this, right? This whole thing divided by this denominator. Okay. So next, this n minus 1, because it is divided here, so I can write this here. So n minus 1, they become cancelled out, and I'm simply multiplying, dividing both the numerator and denominator by n, right? So this is the formula for beta 1 hat TSLS. And why I bring down to this particular scenario, because beta 1 is now separated. So now I can easily prove that beta 1 two-stage SLS is an unbiased estimator of beta 1. So if I applied the expected value on both sides, beta 1 is a constant, so expected value of a constant is the constant itself, so it will be beta 1. And expected value of this second term, right? If I simply don't divide by n, or I do it, that doesn't make any difference. It's just that in some sort of derivation we need this n form and sometimes we don't. So currently I ignore it and I apply the expected value separately. So the expected value, because the starting argument was the instrument and the random error are independent, therefore I can separate out these two expectations. That is, I apply separately expectation on this part and then on this part, divided by this thing, that is the sum of zi minus z bar into xi minus x bar, right? So I've applied the expectation over here. So remember that over here the problem issue was this residual term ui. So we are sort of currently focusing on this. Its expected value is 0, so this term vanishes, and we prove that the expected value of beta TSLS is equal to beta 1, right? Expected value of actually there should be a 1 here as well. That's a small typo. So you write expected value of beta 1 hat TSLS is equal to beta 1, right? So this is written here correctly, right? Okay, so that means that its mean value is beta 1. So from here we can say that beta 1 TSLS follows normal distribution with mean beta 1 and variance equal to this thing. So what is this variance? Let's see in the coming slide. Okay, so this variance of TSLS is the variance of the formula that we just wrote, right? Now I'm using that formula where we have n in the numerator and denominator. So we know that beta 1 is a constant, variance of a constant is 0 plus variance of this part, right? And this is again a constant, so it is squared, right? So now we have, this is covariance of zi and xi square, right? If I consider this denominator part, then variance of summation could be written as, you see, variance of a sum could be written as n time variance of that internal quantity. So this n and this n square cancel and we get 1 by n, and we get variance of zi. Now I have replaced this z bar with mu z. Why? Because we have just proved that in the large sample z bar converges to mu z. So we were analyzing the large sample properties, that's why I replaced z bar with mu z. So we have this formula. Okay, so this is the formula for finding the variance of beta 1 hat TSLS, right? So what does that mean? If you have sample data, you can simply calculate this quantity and you will, or you can not, if not calculate, you can estimate this, and then you will have this formula that beta 1 TSLS follows normal distribution with mean beta 1 and variance this. So on this note, I end today's lecture because I understand quite heavier concepts they were covered in today's video, and I expect that you watch this video at least twice or thrice so that you can, and pause the video intermittently so that you can understand and absorb the difficult and technically demanding concepts that are discussed in this video. Thank you, and keep watching other videos that by the way, on my channel you can see videos on basic statistics. You can also see videos on different topics of econometrics. So those of you who are watching this video, it's highly recommended that you explore other learning videos on this channel. Although there are some, actually on this channel we have different playlists. So if you see the playlist of statistics, that is you will see only those videos that are introductory for the statistics concept. If you see the playlist of humor, that's a different aspect. They are liked fun videos. And if you see the playlist of Econometrics, you will see videos similar to this particular video. So thank you. Keep watching the channel, keep learning, and I expect that, and I really hope that you get benefit from these lectures. Thank you.